Welcome everyone. My name is Pramod Beesal and I am an IIT Delhi graduate. In this video, we are going to discuss about the state space representation of any physical system, and this is a part of control theory. This is our last video for IES syllabus. After this, we are done with the prelims syllabus at least. Okay. So when we talk about the state space representation, so one form of writing any equation for a physical system we have already seen in our previous video. That was our transfer function with related to Laplace equations and everything. Now, if you don't want to use the Laplace, if you don't want to use the transfer functions, then second type of representation that we can have is called as state space representation. Okay. So how exactly will that happen? We are going to discuss that with the help of one example only. Again, the same example. Okay. So let's say there is a force of F input T here, which is giving me some displacement xi T to my system. Okay. Now the equation that I'm going to get over here is going to be F in T will be equal to m d square xt divided by dt square plus d dx divided by dt plus k into x, right? And that is going to be my equation after I balance everything. Now what I need to do here when I am writing the state space representation, the very first thing is I need to arrange them in decreasing order of their power, and or the first value or the maximum power value has to be having a coefficient of 1, so it cannot have m here. So I'm going to rearrange it, so it will become d square xt divided by dt square, right? And what it will be giving me plus t times dx divided by dt, and m will get divided over here, plus k by m xt, and that will be equal to f in divided by m. So that is like our standard representation of the equation. We are doing it standard representation so that it will help us giving the state space representation to our system over here. Okay. Now when I say that I'm going to apply the state space representation, it basically means I'm going to define certain states. Okay. And those states are given in terms of our output differentiations. Okay. So the output is what? X here. Output differentiations, I can say. What is my output here? Output is x. Okay. What is the order of my output or order of my equation? Order of differential equation is 2. Okay. So I am going to have that many states. Okay. So the order of the state is going to give me number of states. That is just for our simplicity to solve these equations. Okay. Now what is there? That there are going to be 2 number of states, and they will be in terms of outputs differentiations. Okay. So first state, we always say that P1, we define the states in terms of P. So P1 is equal to X. Simple. Okay. But I'm going to have 2 states here. So P2 will be equal to dx divided by dt. If the order of my equation was 3 order, then I would have had a third state here also, that will be d square x divided by dt square. We are going to have that example so that you can understand it. Okay. Now these are 2 states. I have defined the states. Now what will happen, that I can say that P2 is nothing but a differentiation of P1 itself. We will always do that. We will write respective value in terms of differentiation of previous value. Okay. So here we cannot write any differentiation, but here I can write. So I will say P2 is equal to dp1 by dt, and for the simplicity I am going to represent them with dots. Okay. So one dot is basically one differentiation with respect to t. Differentiation with respect to t. You already know these terms, right? So dx by dt I can write as x dot, and d square x by dt square I can write as x double dot, right? You already know these things. Okay. So P1 is x, P2 is P1 dot. I have calculated these 2 values here. Okay. And then third, I don't need any third value, but I will say d square x divided by dt square. That is what? Second differentiation of dx by dt. I can write it this way, right? And that can be written in terms of d by dt of dx by dt, and dx by dt is what? P2, right? So we can say it as P2 dot. Okay. We are going to have only first differentials at max, so it will be represented as P2 dot. Now I am going to write this equation in terms of a matrix. I'm going to have a matrix representation here of that particular same equation only. So what are the equation that I'm getting finally? Equation number 1 is that P2 or I will write it other way. P1 dot is equal to P2. That is my equation number 1. Okay, I'm always going to have these equations and that type of equations. And second equation is I'm going to replace all these values with what we have done here. So D square is nothing but P2 dot. So it will become P2 dot. Okay, then plus D by M into next value, that is D by M into dx by dt. What is our dx by dt? Dx by dt was P2, nothing but P2, right? Then plus K by M into xt. Okay, so what I will be writing that K by M into what is xt? Xt is P1, right? And that is equal to our F input divided by M. So what I have done here, I have converted my second order differential equation into two first order equations. Okay, so there are two first order equations which has been derived from our second order equation. So what is we are doing here, we are converting whatever we have, converting nth order differential equation of system into n single order DEs. Okay, that is we are going to do. So there was a two order differential equation and we converted that into two single order equations. Now I can write the matrix representation here. Okay, so how can I do the matrix representation? I can say that P1 dot P2 dot is a matrix of the left hand side, and that is equal to, yeah, I will get them all onto the different side. Okay, so that will be coming out to be, let's say, I'll write it over here. P2 will be equal to F in divided by M minus D by M P2 plus K by M P1. That will be my equation for P2 dot, right? So I'm going to write these equations here. P1 dot is what? There will be some matrix here and it will be written in terms of P1 and P2 only. Okay, so in terms of P1 and P2, in this case we are having no P1, there is only P2. So P1 dot is equal to this multiplied by this, so P1 plus P2 only, and P2 dot is equal to, in terms of P1 the multiple is K by M, so that is our minus K by M, and in terms of P2 multiple is minus D by M. So we have got this equation here. Okay, but still the representation is not complete because we have written only these two values. This value is still remaining, so we will be writing another matrix over here, and the coefficients are already decided as our input value, that is our F in T. Okay, so in terms of F in T, I can say in terms of P1 dot there was no F value, so it will be 0. In P2 I was having a value that is 1 upon M. Okay, now let's see if our equations are correct or not. And if I solve this particular matrix, then I will be having P1 dot is equal to 0 into P1, 1 into P2, and P2 plus 0 into F, and P2. So P1 dot is equal to P2. Correct equation, right? Second equation that I am having over here is P2 dot is equal to, now this will be multiplied by this. So these two values I am getting this plus 1 by M into F in by T. Okay, so very simple state space representation. We will be having one more example so that you can understand it. So don't get confused here. It is anyways a simple example as compared to a three order equation or so. Okay, so this matrix is known as matrix A. Okay, this is our A matrix, which is a multiple of P1 and P2s, and this is known as system matrix. System matrix. Now what is the order of a system matrix? It is always going to be n by n square matrix if n is the order of my differential equation, or if n is the order of my system. Then this is known as matrix B, and we call it as input matrix because we are multiplying it with our input, right? So this is our input matrix, and its order is always going to be n cross 1. Okay, so if n is the order of my differential equation, it is always going to be n cross 1. Now still the state space representation is not complete, so this is just one part of it. The second part comes when we write output also. Okay, so still the output is remaining, right? So I can say x is equal to, in terms of P1 and P2, So that is what 1, 0, P1 and P2. Is that correct? It will always be in this format only. X will always be having 1 here and then 0, 0, 0 or with respect to all of them. Now this matrix is our C matrix. Okay, so here this is our matrix C. So C is what? C is known as output vector. Output vector, and this will always be in 1 cross n order, right? We will be having a D matrix also, but I'm not going to write that here. That can be written in terms of plus some value into F. Okay, so we can have our D matrix here also, and D is known as our let's not worry about that. Okay, and this P1 and P2, this is our state vector. Okay, this is a state vector 2 cross 1. Simple. The state space representation is quite simple. You have to just give a little bit attention to it. Other than that, there is nothing in it. Okay, just hang on a minute. Maybe if you did not understand this question, how exactly did we write the representation here in terms of a state and space, we are going to have one more example so that you can appreciate it better. Okay, but before that, I'm going to define two different concepts here. And one is known as controllability, another one is known as observability. Okay, so as the name itself suggests, it is the control ability. So whether or not we can control our system, that is controllability. If the state of the system can be changed from one value to another in finite time. So there are two conditions here: in finite time and by a finite input, then the system is called as controllable. Okay, so whenever we are doing the state space representation, we have calculated these A, B, C and state matrix. Okay, all those things we have calculated here. When we are talking about the controllability, then what I can say here, I can again define one matrix which will be the matrix of controllability. Okay, and that will be defined in terms of phi C, or the controllability is going to be equal to B, then AB, then A square B, and so on up to whatever is the order of my system. Okay, so up till that value we are going to have it. Now, for example, in the question that we have done above, the question related to our mass damper system, where we had n is equal to 2. We had a system wherein our matrix was a 2 by 2 matrix and so on. Okay, so for that particular case, my controllability matrix will be given by B, AB, and that's it. Okay, so that will be for a 2 cross 2 matrix. For n is equal to 2, I am going to have like this. If for n is equal to 3, if it will go up to A square B, and so on, I can have the matrix of my controllability. Okay, now what I need to do, I need to calculate the determinant of this particular matrix, the determinant of IC matrix, and if that determinant value is 0, then my system will be uncontrollable, means I cannot control my system. If the determinant value is non-zero, means it is a controllable system, I can control the system. Now let's take the example that we have solved above, and we are going to use those equations, and then we are going to see whether the system is controllable or not. Okay, so the A matrix that I had calculated here in this particular case was, what was our A matrix? It was 0, 1 minus K by M minus D by M. That is our A matrix. What other matrix do we need here? B matrix. So our B matrix was 0 and 1 by M. Now I am going to write the controllability matrix. That is our matrix phi C. Okay, so phi C is what? B, then A into B. Okay, so that will be, the B matrix will be coming over here first, that is 0 and 1 by M. Then the multiplication of these two matrices together. So A into B, that order we have to remember here. It is A into B. Okay, so we are pre-multiplying these things, right? A square B, A cube B, and so on. That is not a post-multiplication, because in matrices, pre-multiplication and post-multiplication are very important. We have already seen that in robotics, right? So A into B, when I am doing, so it will be A multiplied by B. So I will be multiplying it here basically. So it will be coming out to be 1 by M. right? And then this will be multiplied, so that will become minus d upon m square, right? Minus d upon m square. That is my A into B matrix. So I will put that here. A B matrix I have put here, right? Then I am putting A into B matrix, and A into B matrix is this 1 by m and minus d upon m square. Okay, so that is how my controllability matrix is going to look like. Now I will check if it is controllable system or not. So I'm going to determine the determinant of this particular matrix. Now phi c is equal to what? The determinant of this matrix is what? This multiplied by this, that is 0, minus their multiplication, and that will become minus 1 upon m square. Now if my determinant value is non-zero, it is non-zero here, right? So phi c is not equal to 0, means my system is controllable. I can control this particular system over here. Okay, now we define one more concept, which is known as the concept of observability. So just like our controllability means whether we can control the system or not, it's the concept of observability is whether we can observe the system or not. Okay, so if the state of the system can be calculated, we are able to calculate the state of the system with the help of output. Okay, we know the output and we can calculate the state of the system, means reverse calculation basically at any instant of time. Then the system is observable. Then we will call the system as observable system. Okay, now similarly we are going to define a phi observable matrix here. Okay, phi o, and that will be given for any nth order system, whatever system, the general system I am having, there will be a C transpose, then a pre-multiplication of A again. Okay, A into CT, then there will be A square into C transpose, and so on up to whatever is the order of my matrix. Now similarly, if I have order of 2, then my phi observability matrix is going to be C transpose into C transpose and then A into C transpose. Okay, now let's take the example again, the same example that we have done. So A matrix was was our A matrix? A matrix was 0 1 minus k by m and minus d by m. That was our A matrix, right? And what is our C matrix? C matrix was 1 0, but what we need C transpose. So C transpose is 1 0, and then we need A into C transpose, means A into C transpose. So that will be what? A into C transpose will be equal to 0 into 1, 0 into 1, so that will become 0, and then this will become minus k by m, right? So that is my A into C transpose. Now what will be my phi observability? This is for our same example that we had. Okay, so phi observability matrix is going to be equal to C transpose first, C transpose it 1 0, then in our next row it is going to be this matrix, that is our 0 minus k by m. Okay, now in order to establish the observability condition, whether it is observable or not, what we do, we say if determinant is non-zero, then it will be observable. If the determinant is 0, then it will be not observable. You have to remember the conditions very specifically here. Okay, so when we calculate the determinant of this particular matrix here, then it is a non-zero value minus k by m, means my system is observable. So if I have any output condition, I will be able to calculate the input conditions on which that particular output can be observed or that can be obtained. Okay, now let's have one more practice question. As I told you initially itself, that we are having a three order system in which this is the equation of the system. We can represent the system with this. X is our input, Y is our output. We need to check whether the system is observable or not, whether the system is controllable or not. Okay, so I'm going to do everything on same page only, so that you don't have to be confused in it. All right, so this is the system. Now what I said initially, that if my system's order is 3, then I'm going to have 3 differential equations. 3 1 order, this will mean 3 1 order differential equations, right? That is what I'm going to have over here. Now how will I get that? First differential equation will be nothing but, first equation will be P1 is equal to X. I'm simply going to assume P1 is equal to X, not X, here Y. Y will be here, right? So Y is our output. So P1 is equal to Y. Second, what I'm going to say, P2 is equal to P1 dot. Simple. And P3 is going to be P2 dot. So I have got 3 variables here, right? Now I am going to write this equation in terms of P3, P2 and P1. So what will be this equation? This is a third order differential, means d3y upon dt cube can be written as d by dt of d square y by dt square, and this is what? P3, right? So that can be written as P3 dot. Now I'm going to write the equations here. So this will become P3 dot plus 4 times, now this is what? d2y by dt square, that is our P3 plus 3 times dy by dt. What is our dy by dt? That is our P2, right? Then plus 2 into y. What is y? That is our P1, and that is equal to xt. Okay, we can have only one differential in our equation, and that has to be also single differentiation. So final equation that I am getting here are P1 dot is equal to P2, P2 dot is equal to P3, and P3 dot is equal to, let's take everything onto that side. So it becomes 2P1 minus 3P2 minus 4P3 plus xt. Okay, now I'm going to do the state space representation. So for the state space representation, the very first equation or the very first thing that I write is what? I'm going to write P1 dot, P2 dot and P3 dot, and this matrix I'm going to create first matrix whose multiples have to be P1, P2 and P3. Okay, they have to be the multiples of that particular matrix, plus there is going to be a second matrix here also, and its multiple will be only input, that means our xt. Clear? So let's get the matrix A and matrix B here. What will be our matrix A and what will be our matrix B? Solving these equations, like looking at these equations, I can say P1 dot is what? Only P2 component is only there, means 0, 1, 0. What is P2 dot? That P3 component is only there, so 0, 0 and 1. Then what is P3 dot? So with P1 I am multiplying minus 2, with P2 I am multiplying minus 3, with P3 I am multiplying minus 4. There are, for P1 dot, P2 dot, there is no component of our x, but in case of P3 dot there is a component of x, and that is 1. Okay, so I have calculated matrix A, I have calculated matrix B, I need to calculate the matrix C also. For that I write yt, which is equal to our output, right? And that is equal to, we need to calculate the matrix, and it has to be in terms of P1, P2 and P3 only, right? So what will be these values? They will become 1, 0 and 0. So this is my C matrix. Now finally I have calculated for the given set of equations, A is equal to 0, 1, 0, 0, 0, 1, minus 2, minus 3, minus 4. B is equal to 0, 0, 1, and C is equal to 1, 0, 0. Now I need to check whether it is a controllable system or not, or whether it is a observable system or not. Okay, and for that I need to write the controllability matrix and I need to write the observability matrix. Okay, so you can do it, right? So controllability matrix will be B, A, B, A square B. That will be my controllability one, and observability will come in terms of C transpose, A times C transpose and A square C transpose. Okay, and if I solve these equations, because this is a third order, so I am not going to get into the details of it, otherwise the calculations will become very, very lengthy. You can check it if you want. Okay, and this will be 1, 0, 0, 0, 0, minus 2, 0, minus 2 and 8. Now I can see if the determinant is 0 or not. So phi C, the determinant of phi C is minus 1, means it is controllable. It is controllable. And determinant of phi O is minus 4, means it is observable. Okay, so there is very clear cut analysis that we have done for the question that we had. Okay, now we will be having one more question here, and that is the last question for our whole syllabus, and we are going to have a 2-order equation only, because 3-order will unnecessarily make our system complex. Okay, so let's say we are already given A matrix as 1, 2, alpha and 6, and B matrix as 1 and 1. We need to calculate the value of alpha, for which the system is, controllable. Okay, or let's say uncontrollable, the system is not controllable, we need to calculate that value here. Okay, so in order to calculate that, we first need to calculate phi c, that our phi c matrix, and that will be what? B and A into B. So let's calculate it. B matrix is 1 1, and A into B will become what? A into B will be 1 plus 2 3, and then this, that will become alpha plus 6. So that is my controllability matrix. Okay, now what I do, for uncontrollable, phi c has to be 0, the determinant value has to be 0, so its determinant means alpha plus 6 minus 3 has to be equal to 0, so my alpha value becomes minus 3, and that is our answer for which the system will be non-controllable or uncontrollable. Okay, so well, that's it, we have done everything here. Okay, also you have to remember one thing from the prelims point of view only, that state space representation is not unique to a system, is not unique for a system. Okay, so if we are having a system, it's not necessary that we get a unique state space representation for that particular physical system. Okay, so that's all for this syllabus. The whole syllabus gets completed here. Mechatronics is complete. I will try to make a revision video as soon as possible, and I will mention the important topics in that again. Well, thank you for watching, and best of luck for your exam.